Yes, here is the title of the talk. Motion maybe is not a very exact word, I'll study. So I'm studying self-locomotion of a body with a rigid surface and variable distribution of mass and of fluid. My co-author is Lieutenant Sergey who did a lot of simulations. Part of this job I did part of this job under the supervision of my PhD scientific advisor, academic Валерий Васильевич Козлов. So first I'd like to start with maybe outlining some historical moments which are concerned with the self-propulsion of bodies and fluid. For a body to move in the medium, it inevitably must exchange energy with the surrounding fluid. If a body is surrounded with nothing, no matter how it deforms its shape, no matter how it redistributes its mass, won't be able to shift its center of mass. Its center of mass will stay fixed. So some exchange of energy with surrounding fluid is required. What are possible mechanisms of such an exchange? It's customary to mention shedding of vortices, viscosity, or we can interact by changing our shape. Shedding of vortices is a known phenomenon. Very few. Much literature is devoted to it. The pioneering and mathematically rigorous pioneering contribution in this field is due to who considered a plate. This is an adjoint view of a plate. They have a traveling wave, so its surface was waving in some manner, and there he postulated past the flow, and behind this wave there was a surface along which the velocity was discontinuous. So he postulated that such a surface accompanies our waving plate, and he rigorously proved that specifying accurately the parameters of these waves, we can force this plate to move forward. There are a lot of other qualitative studies, and so this is a rigorous mathematical treatment of the problem. That's why I mentioned this paper. Another example of use of vortices is depicted in this lower right picture. This is a device from Scott Kelly's paper. From above, it looks like this. This is a ring floating on the surface of a fluid, and there is a cylinder which can be set to rotation with a motor. As the central cylinder rotates and real liquid is not ideal, there are vortices shed from it, and there establishes and settles some circulation around this body. If we impart some velocity to the center of this device, there will appear a lift. So this is a force which caused by artificially produced vortices. Vortices play an important role. Without shadow vortices, there will be no lift and aircrafts will be able to fly. But this shadow vortices is in some sense passive. We can't control this. And this process is controlled as we can control the rate of rotation of this central cylinder. So this is about shedding of vortices. Viscosity, of course, it's another important mechanism. A lot of done about the self-propulsion of microscopic bacteria in the realm of low Reynolds number. Here we should mention pioneering works of Taylor. Lighthill is developed further. The ideas were then developed by Purcell in his famous life at low Reynolds number, and they were recast in a more modern geometric differential geometry language in the paper of Schaefer and Witch. This is viscosity. Until quite recently, until 1916, it was unclear if we discard the following question. There was no definite answer to the following question. If the fluid is supposed to be ideal, meaning there are no friction, meaning there are no vortices, because in an ideal liquid they are known. It's known that in an ideal liquid vortices can be generated. And when the motion is started from rest, can a body just deforming its surface propel itself through the fluid? When viscosity is added, the answer is obvious, yes it can. But what about the absence of friction? For the first time, this result mathematically rigorously was proved in this paper. Benjamin and Ellis considered a nearly spherical body and forced its radius to oscillate, to change in a rather intricate manner, reproducing them as a series of some spherical harmonics, and they rigorously proved that pulsation can be so chosen that the center of the body will move infinitely far. This result was later redundant with in a paper of Sefman, and a more general and in a more general approach can be found in the paper by Gatter and Needham. The radius, they change differently. This radius and this radius, they then change simultaneously. So, of course, the body is supposed to be a sphere. So, it is known that this mechanism can provide locomotion of the body. So, it is natural to ask the question, is this list complete? Can something else be added? So it's to ask the following question: if the deformation of that surface is also forbidden, the liquid is ideal, the motion is started from rest, there is no vorticity, no vortices, no friction. can we just redistribute internal masses, force a body to move infinitely far? Of course, in the absence of liquid, it is impossible since the center of mass is fixed. To proceed, I will, as not all in this room are supposed to know, to be familiar with the equations of motion of a body in the fluid, so let me give a brief outline of the derivation of the Kirchhoff equations governing the motion of a body in fluid. First, let's start with a free two-dimensional rigid body. The problem where it's considered below all are two-dimensional, so this is the only case we need. So, how to set up the equations of motion? It is easy. We should somehow specify coordinates which define the position of the body uniquely. This may be x and y, the coordinates of its center. Alpha is an angle of rotation of a body fixed frame. That we should express the kinetic energy in terms of this coordinates and their derivatives, and then it's easy. We write standard Lagrangian equations. It's from the standard course of applied mechanics. It's clear. And these equations can be then a bit modified. Let us introduce quasi-velocities. So this is our body, and let these V1 and V2 be projections of the absolute velocity of its center onto the axis fixed to the body. And then we write the equations in terms of the coordinates and quasi-velocities. The equations require make this odd look about them, yet they are the same Lagrangian equations. But when written in this form, it's customary to name them Kirchhoff equations. After this substitution, the kinetic energy written in new variables become. Now, transition to the case when this body is surrounded with liquid, if this liquid is added around it, is quite easy. These constant coefficients, which are the mass of the body, should be replaced and should be augmented with added masses. So now, in the new kinetic energy, these coefficients are also constants, but they are not equal. This is the key difference. Everything looks the same, but these two numbers. For this body depicted here, obviously this is a broad side, it's harder for you. But the body did move in this direction, so we have this inequality. And when the body, so if we have just a rigid body, then we should stop here, plug this energy into the equations, and here we are. These are the equations of motion. If the body is supposed to undergo some deformations, for deformations of rather general class, there should be added some linear terms. Lambda sub 1, lambda sub 2 mu are these functions describe this deformation, and they are our control parameters. So, inserting this energy in these equations, we obtain the sought-for equations of motion. Here they are reproduced again for convenience. This is a complete set. There are 6 equations, 3 equations known as the Kirchhoff equations and the kinematic relations. This system of 6 equations has 3 integrals of motion. These are momenta, and this is and angular momentum. Having at our disposal so many conserved quantities, it's natural to use them to reduce the order. These quantities are conserved. C is a constant vector. So we can solve these equations to find the velocities v1, v2, and omega, and finally plug them into these kinematic relations. These two equations is what we needed, as the x and y are the coordinates of the body's center. And our goal is to make them infinite. This is done, and that's how the result looks like. Additionally, we suppose that the motion started from rest, so this constant is 0. Here are the equations. So A1, A2 are constant. We control lambda sub 1, lambda sub 2, and mu. So we have to choose them in such a way that these functions x and y are unbounded. It's natural to assume that the control parameters, like in nature, move periodically. So that lambda 1, lambda 2, and mu are periodic functions with frequency omega small. So the angle of rotation of the body fixed frame is a linear function plus a periodic function. After the alpha is found, we substitute it into the first two equations, and therefore, and integrating them, obtain the law of motion of the center of mass. We integrate these relations and expand the result in Fourier series. So our goal is to make this series diverge. Of course, this can be achieved if one frequency is an integral multiplier of another. The simplest case when this series diverges is the following. The mean value of alpha is 0. Anyway, it's just a very general approach. What are these functions? Could be they arbitrary. How are they connected with the deformation law of the body? This result is specified for the case when the body's surface is rigid and there is a point of mass m moving inside it. This can be imagined as there is a, from above looking at it, there is a raft and there is a bug crawling on it. So how should the bug crawl for the rift to go infinitely far? So to obtain the equations governing the motion of its center and orientation, we do the same steps, write out the kinetic energy, where psi and eta are the coordinates of this bug. follow the previous steps, solve for the velocities, and finally obtain the equations of motion. These x1, x2, etc., they are rather complicated functions. They are not written here. They are rather bulky. So this system can be augmented with obvious relations and using this notation, we can rewrite this system as these systems are well studied in the theory of control systems. For us to be able to steer from initial position to any desired final position, it's necessary to check the following. We take these two vector fields in the 5-dimensional space. We take the Lie bracket of them, calculate a commutator of these vectors with these fields. Then we can calculate nested commutators, and it is known that if these 5 vector fields span the whole space, they are linearly independent at each point, then, according to a famous Cho's theorem, in Russia it's also referred to as Rashevsky theorem, this system is absolutely controlled. So, given any initial position, and given any final position, the bug can move on this body so that these two positions are joined with a reasonably smooth curve. So to check that these vector fields actually span the whole space, we organize them into a matrix and calculate its determinant. The result is as follows. We see that the determinant is evaluated at the origin. We see that the only factor which can be 0 is that one, kappa 1 minus kappa 2. It can be 0 provided A1 and A2 are the same. In this case, everything is okay, and this product is different from 0. So the system is fully controlled.
What is A1?
Is it? Let me see.
No, what is A1 and A2?
And A1 and A2. Oh, very rich. When I talked about transition from the no liquid situation to and this is a free body. A body is immersed in fluid. After the body is placed into a fluid, these constant coefficients should be replaced with other constant coefficients known as added masses.
So A1 and A2 are added masses.
They are mass of the body plus its elements. It's a coefficient that incorporates mass plus elements.
Are they time dependent or are they constant?
They are constant. Why choosing this body fixed frame just to make them constant? Why not using this frame? They are constant. For many ships that could be found in special reference books, but they are like moments of inertia. If a body is not symmetrical, these coefficients differ because it's harder to go through the liquid with the broader side forward than with the narrow side. the body is essentially hydrodynamically asymmetric. Here is an example. Suppose the point inside of the curve moves along this rectilinear, moves along this polygonal configuration. That is how the center of the body will move. It's just an example. So any tick marks, they are removed. There's just qualitative resemblance with what happens.
You said that if A1 is equal to A2, then...
Yes, this is my remark about this. If they are equal, the motion is impossible.
And here?
Here they are different.
A1 is equal to A2.
In the picture. Remark. If they are equal, the motion is impossible.
But is the picture of the body is an ellipse or something?
Yes. If A1 and A2 are different, the fields are independent and the motion is possible.
So this picture corresponds to the upper.
Yes, it corresponds to the upper, not to the lower ones. It's just a remark. We run simulations with viscous fluid. If the fluid is so, this is the body here in these pictures is taken an ellipse with its semi-axis approximately 1 and 5. If viscosity is added, I don't have this picture along with me. I will show other pictures from the viscose case. But here, if we simulate the same thing but in viscose fluid, this strip, this average direction of motion will rotate through some angle. And it's interesting to note that about this remark, that if the body is symmetrical, if this is simply a circle floating on the surface, no matter how a body moves, it won't be able to push this body far enough. What happens if we add viscosity? Now we solved Navier-Stokes equations. We did not replace the friction imposed on the body with some asymptotic expressions, so some phenomenological formulas. So as the body, there are two options for the point mass. Two paths are shown. One of them a polygonal path, and the other is figure-8 path. This is the trajectory of the center of the body for the figure-8 path, and that one is for the polygonal. They are approximately the same. This is another picture. This is a circular body which can't move in an ideal fluid. If we remove vorticity, a heavy line, the body stays in place. It just goes along a figure-8 too. It's centered also. If vorticity is added, so we see this takeoff goes away. Viscosity. It's added, so it takes off. These pictures may suggest that there is some analogy with finite number degrees of freedom dynamical system may exist. If in the course of motion of the body we watch the evaluation of these meta components, which are not conserved now with viscosity, and watch the evaluation of the drag that the body encounters. So we see some attractor-like structures in these planes. There definitely the body is also attracted. There's so we still we're yet unable to explain why is this happening. It's interesting to know that the body is able to move rather far only due to viscosity, because it's symmetric. And the same effect, viscosity, stops it from advancing further. So at the first stage, viscosity helps us, and then it prevents our further motion. This may be explained, but it's not very much convincing that in an ideal fluid, the motion of the body, in the case of ideal fluid, the motion of the fluid, is uniquely defined by the distribution of the velocities on the surface of the body. If, in the ideal case, when there are no friction, if we know how a body moves, we know its velocity, linear and angular, we know everything about the motion of the fluid. In the viscose case, there is history, so the body is somehow captured with this fluid that it initiated. I don't know. So this may be the reason for the appearance of such an odd, attracting behavior. In this connection, I'd like to add that when we try to not to solve the Navier-Stokes equations, but to model the viscose forces, the resisting forces, putting them being proportional to velocity or to velocity squared, none of these pictures we could not reproduce that. So any phenomenological model did not match with what we obtained from the direct simulation of the Navier-Stokes equations. And now, time, 2 or 3 minutes. Okay, so let's stop here.
Questions for the speaker? Yeah.
You want me to give a definition of that?
You say about
The system absolutely controlled.
Since you control the system such that the body will walk something.
So, no, it does not. Look, the body's velocity everybody's velocity should be proportional already to some vectors. So, of course, its velocity cannot be active. Controllability means that if we take a point in this space, one point in this five-dimensional space, any other point, there is a smooth curve connected.
No,
Piecewise smooth.
you can move from one point to another.
I can move from one point to another. I am not sure about my intermediate state.
Intermediate states, not intermediate curve.
About intermediate curve. A curve defines the transition.
Is it possible that between some points the time will be infinite to reach it?
No, because if you look at the proof of the theorem, we simply how we actually connect. I have a picture. I'll show it to you for it's in Russian. That's not how it looks in reality. So we go along integral curves of these vector fields, and it can be proved that we need only finite number of such segments. So the time will be finite.
I want to make a comment about phenomenological laws. If you take linear resistance proportional to velocity, then if you want to move the body and the resistance is linear but anisotropic, so in one direction, in the other opposite direction, the coefficients are different, then the motion is possible. You can drive the body as far as you need. But if the body is symmetric, isotropic resistance, then it is impossible. As for quadratic resistance, even if in the symmetric case, the motion is also always possible. So you can move.
Anisotropy is not needed.
Anisotropy is not necessary. Even in the case of isotropy, it is proved that the motion is possible. You can move periodically your internal mass and have the translation.
But what's his response? His model didn't happen to work.
So my message was the following, that choosing phenomenological models, we could not reproduce and repeat the results obtained directly from Navier-Stokes equations. So I said that we cannot fit any of these models to suit our needs. Pictures obtained for such resisting forces, they differ from what is obtained from direct simulations.
One question. Your problem you cast into a nice framework that you could apply methods of optimization, like time optimal. Have you
To this system, you mean?
Huh? Yes.
To this.
Have you done energy utilization?
I was to show from the engineering point of view, it's not convenient to make a body with a single point. How could we physically implement this body with one point? So there is another setup with a movie separator. That's what we suggested, that at optimization of what we are working at. Let there be 2 points, but which are forced to move along surface. And There are some results concerned with the motion of such a system, and it seems to be more realistic to build a prototype and to see if it will soon help.
It will be a perfect spy boat. No, perfect source of share.
Unfortunately, I have no short of time to speak about that.
I have a comment. There are related papers by Craig Woolsey. Do you know this person? Looking at looking at a three-dimensional version of this. So he's looked at the problem of an ellipsoid in a three-dimensional ideal fluid. I think both with an internal movable mass and also with internal rotors. I think not with locomotion in mind. Within the last 10 years, but more than 5 years ago, so early 2000s. Yeah. I'm sure they're on his webpage, so you can. But I think looking at, he has Hamiltonian models. He looks at stabilizing relative equilibria, so sort of stabilizing certain motions using mass. Possibly not neutrally buoyant, so maybe trying to steer while sinking.
There is no viscosity.
But no viscosity.
And its equations are exact. Without some models. Okay, I will
he has an idealized model. I'm not sure what
I'll control this.
So thank you again to this.